Hey guys, so in this video we're just going to go over briefly what you've already seen in the Khan Academy videos, but introduction to differential equations, just to try to reinforce what you learned and also see it as the textbook sees it. So basically a differential equation is any equation involving the derivative of some unknown function, right? So really you've already looked at differential equations, right? Like you have studied these before. For example, a very simple differential equation is this. dy dx equals x, right? Like that is a differential equation because it involves a derivative of this function y, which we don't know, right? These are also examples of differential equations. Notice they're saying y is some other function of x, right? So for example, y might be like 2x plus 3, right? It's some other function, right? So really here you might have 2x plus 3 or some unknown, some other thing that's a function of x, right? And that goes for all of these as being functions of x. And then this one says we're involving a second derivative, right? These kind of things occur all the time in physics as well as in math. You can imagine here, like this is a very obvious one that we've kind of discussed before. A falling object has a second derivative of, technically this should be maybe negative 9.8 because it's going down. And that's due to Earth's gravity, right? Gravity's accelerating it down at negative 9.8 meters per second squared. It's a second derivative. You could arrive at the position or the velocity function by integrating this once, and you could arrive at the position function by integrating this twice, right? So this is a differential equation that we already know how to solve. Right, and then there's more complicated differential equations that relate to, well, what if I now have a parachute and I'm falling down, or springs and circuits, and a dog chasing a cat, right? In this course, we're only going to study first order differential equations. All that means is you're only going to see a first derivative, right? So you're not actually going to see things like this where there's a second derivative that gets more complicated. Even though we know how to solve the simple ones, the more difficult ones are more complicated. So in this class, only first order, only first derivatives. This is the general form they're going to give you for differential equations, and it may look really weird. So let me just try to give you an example, right? So when you see f of xy, right, like that just means that there's some function that has x's and y's in it, right? So it might be like f of xy might be x plus 2y, right? When you see g of xy, that just means g of the function g has x's and y's in it, right? It might be, let's not use 2 again, it might be y squared over x maybe, right? And so what this is saying is, okay, well we have some function where it looks like maybe x plus 2y times dy dx plus x squared over y equals 0. And this is the form they use because it's equal to 0, and you can kind of see some structure out of it, right? Now typically what we learn when we're solving implicit differentiation is we would always solve for dy dx. Right, so if we do that for this general function, right, imagine we're trying to solve for dy dx, I'll do that down here, you would get, I'm not going to show all these steps because you guys are beyond that, right, you would subtract the g of x function, so you get negative g of xy, and you would divide by the f of x function, so you get f of x y, right? So this is another way of writing it where we actually solve for dy dx. And remember, dy dx is like the slope of the function, right? So you can know the slope of the function if you knew like some of these x and y values, right? So if I do that same thing for this function, basically we would get dy dx equals negative x squared over y over x plus 2y, which of course would simplify algebraically, but that's beyond the point, right? So just an example of something we're going to do is, remember this is the slope of y with respect to x. If I wanted to know the slope of y with respect to x, like if I knew like that I wanted to know the slope at, let's say 1, 0, right, then I could actually plug in 1 for x and 0 for y. Let's not do that because that's going to give me a 0 on the denominator. Let's say 1, 1, 1 in this case, right? If I plug in 1, 1, on the top I'd get negative 1 over 1 divided by 1 plus 2. That would give me negative 1 over 3. And so I would know that the rate of change of this function y, which remember y is a function of x, so it involves variable x. This rate of change of this function at the point 1, 1 is negative 1/3. And this might have some units, right? We might be talking about water coming out of a tank or a dog chasing this thing, right? But the rate of change we know is negative 1/3. All right, solutions differential equations. We know it's a solution if it satisfies the differential equations for all values. Here's that very simple example, right? Here's a very simple differential equations. We could solve this one by integrating both sides, right? If you integrate dy dx, you just get y. And if you integrate x, you get 1/2 x squared plus c, right? Using the power rule. And so basically end up with this function y equals 1/2 x squared plus c, which we already know how to do that, right? We already know how to solve that kind of differential equation. That is called the general solution. Remember, this is a general solution because we haven't specified the value of c, right? So that's a general solution, as it's saying here. If we know initial conditions, right? Like let's pretend we know that y of 0 equals 4, meaning when I plug in 0, I get 4. Then we could get c equals 4, and we would have what we call a particular solution, right? Particular solution, which is just one curve of the families of functions, right? So like, you know, if this would have been 5, there would have been another curve. Basically, it's just one of the many possible curves when you find the integral. So the first thing you need to know how to do is you need to be able to verify that something is a solution to a differential equation, right? So if you're given a differential equation like this, first we're trying to show that this is a solution. So if I know that this is my function, we know how to take derivatives, right? So I could take the derivative of this with respect to x, and I will get dy dx equals 3c e to the 3x, and that 1 goes away because we're taking the derivative of a constant. And then I'm trying to verify that this is a solution, so I could go back to my original thing. I have dy dx minus 3y. I'll go and write it here so you can see exactly what I'm doing. So I have dy dx minus 3y equals 3. Well, dy dx is just this, right? So dy dx is 3c e to the 3x minus 3. Y is just what we had here. Y is c e to the 3x minus 1. And this whole thing should be equal to 3, right? That's just that 3 coming down. And you do a little bit of algebra on this, and you get, all right, we're just trying to verify. So it's a lot of times when we verify, it like seems like, well, why? That's so obvious. Why are you doing that, right? And then these guys would cancel, and you'd be left with 3 equals 3. And since that's a true statement, we know that, yes, this is a solution to this differential equation for any constant c, right? It doesn't matter what this c is. This will always be a solution to that differential equation. So we have the solution, right? We have a way of solving this differential equation. Wants us to sketch the solution curve for c equals +1, positive -1, positive -2. So basically we're just graphing this. Let's go to Desmos for this. Just because it's really a lot easier to see on Desmos. So it's y equals c e to the 3x. Make sure I write this down right. Minus 1. Right, add a value of c. So for c equals 1, it looks like that. And if it was c equals 2, the function would look like that, right? Just a little bit steeper. If c was 3, it would look like that. And you could do minus 1, minus 2, minus 3. Right, so you see if it's negative, it goes downwards. And so those are all the possible functions, right? And then if you were given an initial condition, you would then know, okay, it's this particular one, right? If I knew something about this curve, I might say, okay, well, this is actually the curve I'm interested in knowing. So that's where this comes in. Find the particular solution which passes through 0, 2. Basically what that would be is I would just take my original equation, and I know I want it to pass through 0, 2, so I'm just plugging in 0, 2. E to the 0, 3 times 0 is 0, e to the 0 is 1, so I have 2 equals c minus 1, therefore c equals 3. So really we wanted the one, that positive 3 case here. Really the equation we're interested in is this one. That would be our particular solution. And the last one is find the equation line to the tangent to the particular solution at 0, 2. remember to find the equation of the tangent line, you need the derivative, right? This here is the derivative. So I have dy dx equals negative 3y, sorry, minus 3y equals 3. I want to know what the slope is, so I'm going to say dy dx. I'm going to solve for this. It's solve for dy dx. It would be 3y plus 3. I want to know it's at 0, 2. So I'd plug in those coordinates here. I'd plug in 0 for x and 2 for y. So it'd be 3 times 2 plus 3. And that would give me 6 plus 3 is 9. So this is the slope at 0, 2. I want the equation of the tangent line. So remember, we have this is an equation of a tangent line. In general, it's kind of easier to see it if you look like this, right? So this is the y value at x1, this is the slope at x1, and this is the coordinate of x1. In this case, x1 is 0. So y minus f of 0 is 2 equals the slope at x1. The slope at that point was 9 times x minus 0. So the equation of the tangent line would be y equals 9x plus 2. And we can check, is that actually tangent to this curve? We go to Desmos and we say y equals 9x plus 2. And you can see at 0, 2, this line is tangent, right? It just barely touches and goes on, but it is tangent at 0, 2, right? So we did that correctly. All right, so that's all this example is showing you, like remembering some of these things, because we've done, we've done C and D a lot in the past. Right, next we're getting into slope fields. This is one way that people actually solve differential equations when they're very difficult to solve. Knowing that a differential equation is telling you the derivative, and we know that derivatives tell us slope, we can basically find the slope of the function at any point and then create a graph based on that information. Right, so the first thing it requires us to do is do this thing that we already did up here, right, is go ahead and solve for the slope. We're going to solve for dy dx, right? That's what we did when we were up here. Right here, right, we already did this. And then you can just plug in x and y values at a bunch of points and figure out what the slope field is, right? So that's what's happening here. They were given this as their differential equation. And they're basically plugging in these are y values, these are x values. So this number here comes from plugging in -2 and -2. So you can see that here. If you plug in -2 and -2, you get -2 times -3, which is 6. Hence how they got this 6 here, right? Another example is if you plug in 0 and -1, 0 for y and -1 for x, you get -1 times -1, which is 1, right? Hence how they got this 1. And they did that for all these points. And then what you would do is you would basically graph the tiny little slope that has this value for a slope, right? So think about like a slope of 1. I'm going to use m. If m is 1, you have a slope that looks kind of like this. That's a little bit too steep. Slope of 1 looks kind of like this, 45-degree angle, right? If you have a slope of 2, it should be steeper than that. If you have a slope of 3, it should be even steeper. And the higher this number goes, the steeper it gets. If you had a slope of, like 1/2, then it should be less steep. And if you had a slope of 1/3, it should be even less steep. And if you had a slope of 1/4, it'd be even less steep. And you're not expected to be perfect with these things, because if you're just drawing it by hand, you're just trying to get as close as you can. And you can also imagine if these were negative, right? If I had -1, then it'd be going down like this. If m was -1, I'd be going down like this. If m were -2, it'd be even steeper going down, on and on and on, right? So that's how they created this. We'll go and we can do another example over here real quick, right? If you're just given a blank graph, usually they'll tell you like, I want to go between -2 and 2, x values between -2 and 2. So you'd basically maybe create this chart for yourself where these are your y coordinates. You'd say -2, -1, 0, 1, 2. Here's my x coordinates, -2, -1, 0, 1, 2. And you'd start plugging these in, right? So you try to plug this number in. And in this case, it's x times y. So this one would be -2 times -2, which is 4, right? So at the point -2, 2, you would be trying to graph a slope of 4, which is steeper than 1, right? Maybe 4 looks like that. Here we be plugging in -1 and -2. Again, we're just multiplying these, so we can kind of just do this in our head, right? This should be 3. So if I go to -1, -2, sorry, that was not the right point. -2, -2 is down here. If I go to -1, -2, then I have a slope of 3, which should be less steep than the one I did here. If I plug in 0, I get 0. So 0, -2, 0. Sorry, I got that on. That's this point here. -2, 0 is here. That should have a slope of 0. This should have a slope of -2 at -2, 1, which is here. That should have a slope of -2, which should look something like this. And this should be -4, so up here I should have a slope of -4. And you would keep doing this for all of those points. It's really time consuming, so I'm going to pause it and show you the answer. Okay, here's what that graph would look like, right? This is going to look like this. You can see we had the first side pretty much correct. If you did the rest, you would get the rest. Generally look for patterns, right? You know that if you're multiplying, then if x is 0, then you're always going to get 0. So anywhere x is 0, you should be getting a slope of 0. Anywhere y is 0, you should be getting a slope of 0. So you can go through and fill in every time y is 0, you get 0. Every time x is 0, you also get 0. And you fill out a bunch of points without doing a lot of calculations, right? So you're looking for things like that you can make simple on yourself. The way we would use this to find a solution is if we knew one initial condition, right? Like let's pretend we know that the point on the curve, let's say -1, 2. Let's say we know this point is on the in our solution. Then we could start at -1, 2 here. And we could basically treat this like a river of currents, right? Imagine this is like a current and it pushes you in a certain direction, right? It's actually going to push you in both directions. So one direction it'd push you up like this. And we don't really know what else goes up there because we didn't make that slope field. But it's also going to push you down, right? So as you go down, you can see as I get in this range, the slope kind of flattens out. So that should be kind of flattening out. As I get closer to the y-axis, I end up with a slope of like 0, right? So I end up coming and flattening out slope of 0 as I cross. And then as I go towards the right, my slope starts going back up again, and I might end up with something that looks like this. And if you do it really precisely, you get like a nice curve. We didn't really have enough points to do it nicely here, but you could just following the currents of it, right? So another example is, well, what if I started at -2, -2? What if that was my initial condition? Well, then you'd start down here, and you'd follow this slope thing, and you'd end up with something like this as your solution, right? And then you get these weird situations like, what if I start at -2, 0, right? That's here. If I just started there, then I would just be flat the whole time. I'd just end up like this. And so this is what they're calling an isoline, right? Anywhere where the slopes are always the same is an isoline. So that's that. And that's what they're doing over here in the book is they're just showing you, if you start at a certain point, like let's say, I start here, then I would want to follow those slopes and, get steeper and follow those slopes and get steeper, and you end up with one of these solutions, right? The only place where you don't get like a curve is if you start right on this line, then you just end up with a straight line, right? So that's that. Here they're going to define isoline for you. It's a set of all points on a slope field at which the tangents to the solution curves have the same gradient. So it doesn't have to be 0 or infinity, but that's usually where we want to know it. It's and usually it's like it might be a line or a curve or something anywhere where they always have the same gradient. So for example, here's a kind of complicated differential equation, right? You can see it's in the form g of x y over f of x y, right? Because this is a function of x and y, this is a function of x and y, hence g of x y, f of x y, right? They already created the slope field. What we notice is that anytime the denominator is 0, you would have an undefined function. And so there's going to be an isoline whenever this equals 0, right? And you could kind of move these over and you get x minus 2. And so you can actually graph x minus 2, right? You start at -2 and you have a slope of 1, right? So that means up 1 over 1, up 1 over 1. And you can see that's how they're getting this graph here, is they're graphing y equals x minus 2, because anytime this is true, you will get 0 in the denominator. And you can see here, a slope, if you get undefined, it's an undefined slope. Undefined slopes are vertical. So you can see anywhere this line passes, you have a vertical little slope on there, right? It's completely straight up and down. Right, another thing we might look at is, well, when are the slopes equal to 0. Like it's basically what we're talking about over here. If like quick ways to do this is if you look, when is it 0? When is it undefined? So we want to know when is this 0? That's going to be when the numerator is 0. And so you'd set the numerator equal to 0. When does this equal 0? Well, it equals 0 when 1 equals x squared plus y squared. That's just the equation of a circle with a radius of 1, hence this, right, radius of 1. And you'll notice that anywhere on this circle, the tangent lines are horizontal, meaning they have a slope of 0. So this is the iso line for all slopes that are 0. You could do the same thing for all the slopes that are 1, all the slopes that are 2, all the slopes that are 3. But these are the most interesting ones. Well, the most interesting ones are when the slope is undefined and when the slope is 0. All right? So moving on, another example, we have consider the differential equation given here, verify that this is a general solution, right? Maybe we can just quickly go through this example so we don't have to take so much time. Basically what you're going to do is you're going to take the derivative of this, right? So that's what they did here. That's the derivative of this function. You have to use chain rule and the rule for differentiating e to the x. You simplify it, right? And then you are plugging it into the original thing up here, right? We know that y is ce to the x squared, so we're replacing y with ce to the x squared, right? Putting this right there. And if you, so then you get, no, that's not what they did. They just showed that, hey, this is ce to the x squared, which is y, and so you end up with replacing the c to the x with y because they're the same thing, and you end up with dy dx equals x times y, which is what you started with. So they're kind of doing it in a different way. You could do it the same way that we did previously as well. Construct the slope field. You know, you're gonna have to apply. You're gonna have to for x, y from 0 to 4. So you'd have to, you have to create this, and you have to go 0, 1, 2, 3, 4. These might be my, actually like x values here better, but 0, 1, 2, 3, 4, because then I can read it x, y. That's why I was getting confused before. This is actually the one we created up there, right? Except different values here. So it's x times y, right? That's our slope. So 0 times 0 is 0. 0 times 1 is 0. 0, 0, 0. Anywhere it's 0, it's always going to be 0. These are iso lines for 0 slope. And then here, 1 times 1 is 1. 1 times 2 is 2. 3, 4. 2, 3, 4. And you just create a graph from 0. All these points would have 0 slopes, and then you'd have increasing slope as you go. It's all pretty straightforward. What's a little bit more complicated is Euler's method of numerical integration. It's actually more important and more useful than slope fields, right? Slope fields are tedious. You would need a computer software system to like do this for you if you're actually going to try to find solutions. Euler's method is also tedious, and it's also something that you usually use a computer algebra system for. But we want to understand how it works, and you're expected to know, you're expected to be able to use it to find certain solutions. So let's do this. Okay, it's really a lot easier to understand Euler's method if you have an example. Let's go over the brief idea first. The brief idea is if you know a starting point, right? So let's imagine I'm trying to reconstruct the graph of something, and I know that it starts maybe here. And they're going to call this, oh no, computer's acting up again. Okay, we start at some point which they're going to call x naught, y naught, right? The starting point. Basically, if I had some differential equation, right, dy dx equals, like we saw before, g of xy over f of xy, which again, is maybe it's just like x over y or something. If I have this differential equation, I can figure out what the slope is at this point, right? I just plug in the x and the y and I know the slope. So let's pretend the slope was this. Right, I'm going to use this slope for a distance of what we call h, right? So I'm going to use this slope for a distance of h. So I'm going to just say, oh, well, the slope here is whatever I found here. I'm going to draw that slope for a distance of h, right? And that puts me here at a new x value, right? So now I have a new x1 and I have a new y1. You can imagine, well, how do I get this x1? Well, I just started at x naught and I added h, right? So in other words, x1 is just basically x naught plus that h. How far did I choose to go? And how big you choose this determines how accurate it is. It also determines how many iterations you have to do, right? If I choose this to be really big, then I'm doing this slope, and it's not going to be as accurate as it would be if I chose it to be really small. If I choose it to really be very small, then I have to do a lot more calculations, right? How do I find the y value? Well, the y value is determined by basically the slope, right? Like how much up and how much over did I go? We'll talk about that in a second, right? And then I could go here, and like now that I know this new point, I could take this new point, x1, y1, plug it into my slope function, find a new slope, right? So let's pretend my new slope looks like this, like very steep, right? And again, I'm just going to go h units. We usually keep it, constant. I'm going to use this slope for h units, and that's going to put me here, which is a new x2, y2. And again, well, how did I get from x1 to x2? Well, I just added h units, right? I just added another h. So x2 would just be x naught plus h, and the y coordinate would be determined by how much up and over I went, right? Like how much up in the slope there was. So you can see that here it's just the value of h times the function x1, y, or whatever value you're on. Again, an example is going to be very helpful here. And you would just continue to do this until you get, basically maybe you get a curve that looks like this. And it ends up being these little linear pieces that create a general form of the curve. If you chose an h really, really small, then you'd have a better look at that curve, right? So it's a general idea. There's some things that we already talked about. The step size, if you make it smaller, that h, you'll have a better approximation. If the gradient is large, you have a not as accurate, right? So like you can see, when I had a bigger gradient, this ended up going kind of farther, which means it'd be less accurate. All right, so let's look at an example. We're going to be given the differential equation. You might ask us, like, why don't I just integrate this and get x squared over 2 plus y squared over 2? Well, the problem with that is you're integrating x and y's with respect to x and y when they're not functions of x and y. So you can't just do that, right? Like you have to know what you're integrating with respect to. So we're given an initial condition of 0, 1, right? So I know that I am here when I start. 0, 1. I know that my differential equation is x plus y. So what's the slope at 0, 1? Well, it's 0 plus 1 equals 1. So here at this point, I have a slope of 1, which means I'm going to go up 1 over 1, right? How far am I actually going to go with this? Well, we want a step size of 0.2, right? So we're going to actually count by 0.2. So let's call this 0.2, 0.4, 0.6, 0.8, 1. Right? And so the x value is going to go over by 0.2. What we need to know is how far up should I go, right? So the slope is 0.2. Sorry, the slope is 1. So if I'm going to go over 0.2, I should also go up 0.2, right? If that's the slope of 1, then the rise of the 1 should be the same. So this should be 1.2, right? So I'm saying, oh, my function looks like this here. My new coordinate here is now 1.2, 1.2. Right? No, it's not 1.2, 1.2, sorry, it is 0.2, 1.2, right? Because the x coordinate is 0.2. I would then plug this in, right? So now I want to know what's the derivative at 0.2, 1.2. You plug it in, you get 0.2 plus 1.2 is 1.4, right? So the slope is now 1.4, right? Which means, okay, well, I know I'm going to go over 0.2, which then puts me here. How far up should I go? Okay, so how far up should I go? Well, we're trying to do slope, right? If you remember, slope is change in y over change in x, right? And we know that our slope should be 1.4. We already know that our change in x is 0.2, right? We're going over 0.2. So this is 0.2. So we could solve this by multiplying both sides by 0.2, and you'd get the change in y is 1.48. So this new y coordinate should have a change of 1.48. It was already at 1.2, so my new y coordinate, right, my y2, we're on y2 now, should be where I started, which is 1.2 plus 1.48, which is 2.68, right? So my new y coordinate should be at, let's see, that's 1.2, that's going to be a bit up here. no, sorry, this is not 1.48. I end up getting 1.48 when I'm all done. So we need to do 1.4 times 0.2. Should just be, was that 0.7 or something? Let me check. No, it's 0.28, right? So this is 0.28, and then you add that. You're going to add that here, right? Because the change in y is 0.28 to the original y. This is like the y1. I'm going to add the change in y to what it was before, and then I'm going to get 1.48. So from this, which is y1, I'm trying to find y2. I know I go over 0.2. I now know I go up. All right, now I know I go up 0.28, and I should end up at 1.48, right? So I should end up at, this is 1.4, this is 1.5. I should be pretty close to 1.5, which is 1.48, which is there. Right, so this is now 0.4 is the x-coordinate, and the y-coordinate is 1.48. So I don't know if you recognize where I'm getting this, but where this is what's happening here. But the next y-coordinate, so the yn plus 1 is basically coming from the yn plus the change in x times the change in x times, what do we multiply it by? We multiplied it by 1.4, which was, we got 1.4 by adding 0.2 plus 1.2. Times the slope. This was the slope, right? So this was the dy dx at that value, right? So for example, the next one I can kind of do more formulaic, right? The next one we want is y3, right? So y3 is going to equal y2 plus the change in x, which the change in x in this case is always going to be 0.2 because we decided that in the beginning, plus the slope at that value, which is what we need to figure out, right? So we know the slope, or we need to figure out the slope for y3. So our dy dx equals x plus y. We're going to plug in the known point, so we're going to plug in dy dx at 0.4, 1.48. So this is, you could say this is the dy dx at the point at like n plus 1, right? The one that we, so at n, sorry, the one that we already know. You plug this in and you get 1.4 plus 1 is 1.88, right? So this times 1.88. And you do this, and then so then we know y3 is y2. Y2 up here was 1.48 plus whatever 0.2 times 1.88 is, 0.2 times 1.88 is 376. And so the y coordinate is going to be 1.856, right? So the new y coordinate is 1.856. So we could go up here and say, okay, the change in x is easy, right? We just go over 0.2, we'd be at 0.6. The next one should be 1.856, 1.5. Sorry, that would be 1.6 if I'm doing this right. So this is a little bit off. Let's make this one go down a little bit, because we should be at 1.5, which is about there. Next one should be at 1.88, which is a little bit up here, right? And you have the next piece, and you would continue doing this until you got as far as you want to go. And you can see we were getting those new y values fairly accurately up there. You know, we had 1.2, 1.48, 1.865, which is this one. 856, sorry, and if you continued, you ended up there, right? So that's how you do that. It takes some practice, and really, I struggle to like memorize these formulas. What I find easier is just thinking about the process, right? Like you're plugging in the point into the differential equation and evaluating it, and then going up that amount of slope. It makes it a lot easier, right? So what I'd like you to do is these problems 1 through 8.